Section 8.1 is about multiplying monomials. And first we need to know what a monomial is. A monomial is a number, a variable, or a product of numbers and variables. And remember, product means multiply. So some examples of some monomials: you've got a number, 2, a variable, x, the product of variables, or the product of a number and a variable, or the product of a number and two variables, or the product of a number and a variable with exponents. So all of those would be considered monomials. An expression involving division is not a monomial. Now I have to clarify that a little. Here it looks as though we have some division, but specifically you can't divide by a variable. So if there's a variable in the denominator, then it is not a monomial. Okay, so you can divide by a number because then that can be changed into a fraction, but you can't divide by a variable. So if it involves division with a variable, then it's not a monomial. Or an expression involving addition or subtraction is not a monomial. So some examples: 2x plus y. That has two terms. Here's one term, here's another term. That's actually what we call a binomial because it has two terms. Or x over y is not a monomial. Okay, so there's some examples of some monomials and some that are not monomials. We want to complete the table here in order to discover a rule for multiplying two powers with the same base. So if we were to expand the first factor, that would be like 2 times 2 times 2 times 2 times 2. 3 of them and 2 of them. Oops, I was supposed to expand the second one here. Let's get rid of that, sorry about that. And the product then would be 2 times 2 times 2 times 2 times 2. And we want to write that product with exponents, so that would be 2 to the 5th power. Okay? So I want you to complete the chart on your own here. Follow exactly the same thing we did in the first one and do them for this. And then see if you can come up with a rule for multiplying any of the two powers with the same base. Go ahead and push pause and give that a shot. All right, so the rules, hopefully you got 3 to the 7th over here and x to the 7th, and you can see all we're doing is adding the exponents because we're basically adding how many factors there are here. So all we do here is add the exponents. So let's do some examples. Actually, why don't you try these examples on your own? Push pause, come back, and check them. Okay. All right, what did we get here? We should have x to the 9th, 7 plus 2 is 9, m to the 26th, a to the 22nd, and 2 to the 110th. Oops, and I think we adjusted this, changed this to 2, just a plain old 2. Sorry about that. So what I want to make sure you understand is that if there is no exponent on it, it's understood to be 1. So you probably had 209 here. That's because, or 109, because I forgot to add this one here. So 2 to the 3rd times 2 to the 6th times 2 to the 100th times 2, that'd be 2 to the 1st. And then when you add that all up, we get 2 to the 110th. So anything that doesn't have an exponent is understood to have an exponent of 1. Now let's try some examples if there's a coefficient in the front. What if there's a coefficient in the front? Like 5 and 2 and 4 and 4, 2 and -5, -6 and -10. Those are called coefficients. And what if the bases are different? We've got just x's here, but we've got a's and b's here, m's and n's, x's, y's, and z's here. So what do we do there? Now, we want to continue to follow the same thing we always did from, junior high or earlier, actually much earlier. This still means 5 times 2. Pretend there's no variable there. That would just be 5 times 2, okay, with parentheses between it. So with the coefficients, we still do exactly what we always did. If it's a multiplication problem, we multiply them. So 5 times 2 would be 10. And then for the x's, we add the exponents, x to the 12th. So 10x to the 12th. You're going to do exactly the same thing for all three of these. So why don't you give those a shot? Go ahead and push pause. We'll come back and check it. All right, so let's do variables first because that's the easiest. If we have a to the fourth and a to the second, we get a to the sixth. And we have b with no exponent. Remember, that's understood to be 1. And b to the third would be b to the fourth. What do we do with the coefficients here? Now here we have a 4 and a 4 to the fifth. These did not have exponents on them, so we just multiplied them like old school. But this 4 has an exponent on it. But they have the same base, so instead of doing straight up multiplication, we're going to continue to use these exponent rules that we learned at the top here. So this is really 4 to the first, this is 4 to the fifth, so this becomes 4 to the sixth. And you do not need to expand it, just like we didn't expand these here. As long as you only have one base, one coefficient base, it doesn't need to be expanded. You can leave an exponent form. All right, here we do 2 times negative 5 would be negative 10. M to the, remember that's first, plus 3 is m to the fourth, and n to the 8 plus 12 would be 20. And over here, negative 6 times negative 10 is 60, x to the 1 plus 3 is 4, y to the 1 plus 4 is 5, and then the z doesn't combine with anything, so it comes down. So we're just multiplying the coefficients, adding the exponents of like bases. This is the exception right here. If they are bases that have exponents, and they are the same base, then you use the exponent rules instead of just multiplying them. Okay. What about if we want to raise something to a power? That means raise it to an exponent. So we have a product in here, or a monomial, and we want to raise it to an exponent. So let's see what happens. If we expand the factors, this really means 2x squared y times 2x squared y, because the 2 says there's 2 of them. And then we just use the rules that we learned up here. So 2 times 2 is 4, or you can write 2 squared. Let's write 2 squared for now. X squared times x squared would be x to the fourth, and y times y would be y to the second. Okay. You can do exactly the same thing here and here. So this one says to the third power, so we write it out 3 times. Which is no fun, which is why we will eventually figure out what the rule is. So we have 4 times 4 times 4. Let's leave that in exponent form. That would be 4 to the third power. M to the third, m to the third, m to the third. 3 plus 3 plus 3 is 6. Sorry, 9. And then 2 plus 2 plus 2 is 6. All right. And this guy, we have an exponent of 2, or a power of 2, so we write it out twice, which again is no fun. That's why we're coming up with a shortcut here. And then we multiply them. 7 squared times 7 squared, that'd be 7 to the fourth. A to the third would be a to the sixth. B and b would be b squared, and c to the fourth. So suppose we didn't have this. How could we look at this column and figure out what the rule would be to get over to this column? So take a moment to look at that. See if you can figure out what that is. Okay. Basically, if we want to raise a monomial to an exponent, what ends up happening is we end up distributing this exponent to each of those exponents. Now the 2 didn't have an exponent, so it just becomes 2 to the second. We just pass this exponent out to that 2, so it's 2 to the second. But here, this x squared has a 2, so 2 times 2 gives us 4, and then we pass the y out, or the 2 out to the y. Let's look at this one. So this would be 4 to the third, because we pass it out, and then 3 times 3 makes that m to the ninth, and n to the sixth. And this one, 7 to the fourth, multiply those two together, a to the sixth, multiply the exponents together, b squared, and c to the fourth. So the exponent gets passed out to every single factor in the monomial. 2 is a factor, x is a factor, y is a factor, or each base, however you want to think about it. And so on the back side, to raise an exponential number to an exponent, to raise a monomial. That's the other thing we could write here. We just distribute the exponent to each base. And when we do that, we multiply. So I want you to look over these next four. Oops, sorry about that. There we go. Distribute the exponent to each base, and we want to remember to multiply. So I want you to try these. They should take you a very short amount of time to do that. Go ahead and push pause and give those a shot. All right, so we're just passing it out. We want to multiply, so that'd be 4 to the 10th, z to the 24th, x to the 4th, y to the 4th. Make sure you pass it out to every single base inside. And this becomes 2 to the 3rd, x to the 6th, y to the 9th. Boom. So those are your exponent rules, and they all seem simple as you're doing them individually, but we start to get them confused when we do them all together. We mix them up. So we have a stair-step rule that can help you organize your thoughts. So it says over here, whatever math operation you're applying, begin at that step. When dealing with the exponent rules, go one step down to remember what to do with the exponent. So let me show you how to use this while we work through some of these examples. This is a multiplication problem. So here are our stair steps: exponent, multiply, addition, nothing. It's kind of like the order of operations, but we skip parentheses. We go to exponents, multiply, skip division, go to addition, subtraction, and then we got nothing here. So we're using the exponent, multiplication, addition, and nothing. So they go in the same order as the order of operations. We just don't need all of them for exponent rules. So this is a multiplication problem. So that means if it's a multiplication problem, I start on the multiplication step and I go down a step, and that's what tells me what to do with my exponents. So these are exponent rules. So the 2 and the -7, they don't apply to this stair step. We just multiply them like we normally would. That'd be -14. With the x's, though, those are exponents. Those have exponents on them. So the stair step says we add the exponents. So we get x to the 6th, y to the 7th. Okay. Number 12, this is all multiplication. So again, we start on the multiplication step. We go down a step, which reminds us to add the exponents. 8 plus 4 is 12, plus 10 more is 22, plus 3 more is 25. Done. This one has an exponent on the outside, so we start on the exponent step here. And we go a step down, which tells us to multiply the exponents. So we always go one step down. So this is -6 to the 2nd power. We're going to have to talk about that. And m to the 6th power. So as you distribute it over those parentheses, you always multiply. Now let's talk about this. -6 to the 2nd power, that'd be -6 times -6, which would be +36. So here's the rule of thumb. If you take a negative number and you raise it to an even exponent, like -6 raised to an even exponent, the negatives are going to pair up and it's going to become positive. So it would technically be +36. We want to keep it in exponent form, so really -6 to the 2nd power is +6 to the 2nd power. Or you could write 36m to the 6th. But you have to remember that if it's a negative number that you're raising to an even exponent, then the negatives will always pair up and make it positive. All right. The next thing we want to do is look at 14. This is multiplication. We have to be a little careful though because there's different bases here. Multiplication says add the exponents. So we do the a's first. There's only one a, so we just bring it down. We can do the x's first if we're going alphabetical order. And then y to the 8 plus 3 is 11. This one, again, it's a multiplication problem, so we're on the multiplication step. Oops. We go down a step. I'm trying to show you this. Multiplication, go down a step, so we're really going to be adding. So this is 2 to the 7th and 2 to the 1st. We don't want to multiply the 2's together. We have 7 2's and we add one more 2, so it's going to be 2 to the 8th. A to the, add the exponents, and b to the 1 plus 3 is 4. And the final one, we're raising to an exponent, so we go a step down, which reminds us to multiply the exponents. Multiply. If it doesn't have an exponent, we just tack it on. Well, if it doesn't have an exponent, technically it's 3 to the 1st, and 1 times 5 is still going to be 5 anyways. P to the 25th, Q to the 35th, R to the 5th, and T to the 20th. Now the R and the T, some people look at that and they think, oh, it's only one piece. There's just no space because there's no exponent on the R, but every single base is its own separate entity, and that exponent gets passed out to every single one. If anything was confusing there, just go back and rewind it, watch it again. Good luck.